All right. Okay, so welcome again. We continue with the course. Um, so last time we just review everything that you should know from probability theory, like the basics on probability theory. All right, and uh, actually there's a book here in English. It's called Introduction to Probability Theory, I think. Introduction to Probability Theory. I don't remember the author, but you can get that book from the library. And it's a so the topics in that book are basic, okay? So you are not going to get really theoretical things from there, but it's very useful. So if you have like questions related with the meaning of topics like expected value of or random variables or something like that, you can just check that book, and I think that everything will be clear. Okay, so you can get that book on physical, so you don't have to download anything. You can get it from here, from the library, and that's it. All right. So yes, but don't forget. So everything that is here on this book is basic, like very basics on probability theory. That's why it's called Introduction to Probability Theory, right? Okay. So now we review everything related to basic probability theory, to discrete probability theory, and this semester we have to study general probability theory, or theoretical probability theory, let's call it that way. So the first thing that we have to do, the first thing that we have to deal with is measure theory, all right? So measure theory is a full course, 1-year course that some of the guys from the Russian program study. So we are not going to study everything they studied during that year, of course. I'm just going to recall some theorems and some results, very important, that we need to understand the meaning of a probability measure, right? So everything, of course, begins here, always, right? So we have the probability space. We know that this is the sample space, we know that this is a sigma algebra, and we know that this is the probability measure, or this is just the probability. So this word measure, right? So this is the probability measure. The word measure is not related only to probability theory. The word measure is related to calculus. So if you want to find some integral, right? So you already know all of this from calculus. If you want to find the integral from a to b, right? Oh, this is the function f of x. So what is the integral of this function? So what is the meaning of the integral from a to b of this function? Yeah, is this area, right? So this area under the line. So this area S. So how do we calculate that area? To calculate that area, how did you calculate that area? How did you compute that area? How did you find this integral last year in calculus? Well, 2 years ago, your first year. All right, yes, but what do you need to do here? Yeah, so you have to divide all of this into some intervals, right? Some little intervals, AI and BI, right? You have to divide these intervals and you have to make them very small. And then you have to multiply with the function, right, on this point. And you have to sum up everything. And this thing from here, so the distance, so BI minus AI, you call this the measure of this interval, right? The measure of the interval AI BI, the Lebesgue measure of this interval. So just the distance, all right? The distance between BI and AI, okay? And just like that. So you define something called the Lebesgue measure. I think you should have. Yes, so you have heard about that, the Lebesgue measure. And also you started with the Jordan, let me write it over here, with Jordan measure. Right? And you did all of that just to find some integrals. So here we have to do exactly the same, but so we have to define what a measure is in general, right? Because measure is probability, so it's exactly the same. So actually, probability theory is somehow calculus, right? So you will get from probability theory, you will get the basics to what's the name? Functional analysis, I think is in English, functional. So after calculus, the course that you get after calculus, right? Because you don't work anymore with variables, but you work with functions. So instead of working with variables x, like here, you will work with functions. Okay. All right. So let's just continue. So let's make just a brief introduction to measure theory. And let's start with the first thing. So measure theory studies how to assign to each set a measure, right? So we have some sets. I don't know, this is set A and some set B. And we have to assign some measure, right? Some volume, some area, okay? But we have to define what kind of sets we need. So the first kind that we need is called a semi-ring. Semi-ring. So a semi-ring is a family, so this is a family of sets, and let's call it S, right? Semi-ring. So a family of sets such that the first condition is that the empty set is an element of S. The second condition is that if A and B are elements of S, then the intersection of A and B is also an element of S, right? And finally, if we have the set A and the set A sub 1, which are elements of S, and such that A sub 1 is a subset of A, then there exists some collection of sets from 2 to n such that A is just the disjunction union of these sets from 1 to n of AI. Okay, so this is the definition of a semi-ring. So the first one is that the empty set is an element of S. Okay, this is an easy one. The second one is that every time that we have pairs of sets, the intersection of this set, which is a set as well, is also an element of S. And the final one, it looks like this. So if we have A, right? So this is A, this is some element of S, of this semi-ring S, and we have, this is A1, right, A sub 1, then we will find some, and let's, with a different color here, yeah, we will find A sub 2 and A sub 3 and A sub n, right, such that so, and they don't intersect, right? So here AI, the intersection of AI with AG is empty for any I and G different. Okay, so these sets don't intersect, and the disjunctive union of this set is going to give us A. All right, this is a semi-ring. Okay, good. Now, yes. So we already defined what the semi-ring is. Uh, and we can say, so let me call that definition. Well, that is not the definition. So we, how to say it? We say, let me write like that. We say that S, so a semi-ring, has an universal set if there exists some set E, let's call it E, such that this is a set from S and no, nothing, but such that for every AI in S, no, the intersection of E, just a second, I'll formulate to say it. Yeah, so we have that for every okay. Yeah, for every, how do we, no, like, very good. Let me just 6 over here. So for every subset of S, for every collection of S, for every element of S, yes. So for every element A of S, we have that A is a subset of E, right? So we have a universal set, a set which contains all the other sets, okay? So we have a semi-ring, and then we have a semi-ring with a universal set, okay, E. Then, after we got this set, this semi-ring, we can define a ring, R, all right? So, a family, so this is a family of sets such that, so we need two conditions to be whole. The first one is that the intersection, so for every A and B, which are elements of R, we know that the intersection of A and B is an element of R. So this is the first condition, the intersection, and as you can see here, we have this condition here as well. So for both cases, for the semi-ring and for the ring, they are closed under the intersection, okay? And the second condition is that for every A and B in R, it holds that the symmetric difference is also an element of R. So do you remember what the symmetric difference is? I hope, right? This is A, this is B. The symmetric difference is this set. Yes? Okay. And in the same way, we can define a ring with a universal set. So, so here, let me write like this: a ring R with an universal set E is called an algebra. Okay, so we already came to the definition of an algebra, right? So our final goal, of course, is to define what the sigma algebra is. So we want to study measures, and we want to study the measure over the sigma algebra. So we need to define this set called sigma algebra. Where is this coming from? So here we are trying to construct this set, which of course, I can just tell you a sigma algebra is a set for which some properties hold, but how do we get this set, right? It's not that easy, of course. So we get it like this. First, we define the semi-ring, then we define the ring, and a ring with a universal set is going to algebra, okay? So we already get algebra, that's good. And now we can see the following. Now we can see that, so this is the first, let's call it claim number one, that and if we have some ring, so if R is a ring, then first we have that R is a semi-ring as well, and the second condition is that the union and if for any A and B in R, we have that the union of A and B and the difference of A and B is also an element of R. Okay? The complement of the no. Symmetric difference. So this set. Yes? No? So what's your question again? Just so the complement of the intersection. Yeah, that's the way we prove it. Yeah. So it's basically A union B. Yeah, it should be. All right, so we have that. Now we can prove it. How do we prove it? So the first one, let's prove it, okay? So let's prove that R, if we know that R is a ring. So I think that this is like the first and last thing I'm going to prove. I'm going to prove just like two things, but I will have a lot of theorems, okay, which I'm not going to prove because we don't need that. So this one we need it because it's important, okay? So we have that R is a ring, and we need to prove that this is a semi-ring as well. So what's the first thing that we need to prove? That's not here, right? So what's the first thing that we need to prove? If we want to show that R is a semi-ring as well, we need to prove that the empty set is an element of S, right? So how do we prove that the empty set is an element of R? We know that a ring is closed under the symmetric difference, right? And what's the symmetric difference of a set with itself? The empty set, right? So this is just the empty set. So since the symmetric difference of A with itself is empty, then the empty set belongs to R. So the first one is okay. Now, we have to prove that the intersection belongs to R. But by definition, we know that the intersection of every pair of sets belongs to R. So that's proven, right? So that's given already. So A intersection B is an element of R. That's okay, right? And finally, we need to prove that we can find always this complement, this, right, like this set here, which give us A. The disjunctive union give us A. So all we have to do, so first of all, let me prove this one. And using this one, we can prove this one, right? So A union A minus B. How do we get that one? So you already proposed something. I forgot what you said. So how do we get the difference using just symmetric difference and using intersection. Yes? So is this clear? Yeah. So we know that A intersection B is belongs to R. Then we have two elements from R, and we know that the symmetric difference belongs to R, so it means that all of this belongs to R as well. So it means that A minus B belongs to R. Yes? So we prove that A minus B belongs to R as well. This? Okay. We can express A minus B using this. Is this clear? Why, right? We know that A intersection B is an element of R because it's given, right? And we know, so it means that this is an element of R. So we know that A is an element of R. And so the symmetric difference of two elements of R is an element of R. So we have that this is an element of R. Okay. And now the third one is that yes. So we need to prove this. So let me write it over here. How to prove it if we already know this? So we know that for any A, if A is an element of R, then and it's given some A sub 1, which is a subset of A, yeah, and this is also an element of R, then we know that A minus A sub 1 is an element of R. Yes, because we prove it here, the difference is an element of R. So it means that A, which is equal to A sub 1 union with A minus A sub 1 is also an element of. So we got it, right? So this is an element of R, and this is the set that we need to complete this. So we always can find such set for which we complete the whole A. Yeah? Is this clear? Oh? Because we say it that way. So we have A and A sub 1, and both are elements of R, right? So that's given. For example, like it's given on the definition of the semiring. So we have two elements on the semiring, and one of them is a subset of the other. Okay? Good. So we proved this. And now we have to prove that the A union B is also an element of R. How do we prove this? So we need A union B. A union B, as far as I can see, just A intersection B union, no. A intersection B, wait, A, how? I just forgot. A minus, A, yeah, but that's what we have to prove, union, right? So just let me see it. Okay. Yeah, it's like this. Okay, we can show it here. So we have A and B, and we need A union B. So the first set we have is this one. This is the symmetric difference of A and B. And then we have the intersection, so all of this. And what's the symmetric difference between them is all of it, right? Because they don't intersect. Yes? Yeah? is the A union B, because the intersection between A uh, A minus B, well, A symmetric difference with B, and A intersection B is empty. So, right, like here, A intersection B, A minus B intersection with A intersection B is empty, right? So the symmetric difference is all of it. Yeah. Yeah, it's all of it. So all of this is the symmetric difference. Yes. Because the intersection is empty and complement of intersection. Yeah, yeah, that's the difference. You should know that from this course logic from the first year, right? No, that's different. So A minus B is different from A symmetric difference with B. Yes. So these are different. You know that, huh? Okay. What do you mean, any elements? Well, yeah, any such element that we get like this. So if R is a semi-ring, or the union of every pair of the difference is an element of R. So sure, yeah. So what is R and what is this is a family of sets. So this is, for example, R. So this is A here, this is B, this is C, this is D, right? So R subset of, no, why? I don't get what we are only working with two sets, A and B. Why do we need a third one? Yes. Which C? We don't have C. All right, so let's take the symmetric difference between A and B here. It's going to be this. Yes? And why should it be? But they are not in A and in B. So by definition, yeah, I see that this symmetric difference between A and B are all the sets in A and in B, which are not in both of them at the same time, right? You see it? Okay. Good. So we proved that. So we have a semi-ring, we have a ring, we have that the ring with universal set is going in algebra. Okay. Mm, what else do we do here? Just a second. Okay. Well, we have some important things. Uh-huh. Okay. Claim number one. So let's do this fast. No, number two, I think. Okay. The intersection. Yeah. The intersection of any family of rings is a ring. Okay, so if we have R1, R2, and R3, somehow imagine, right, that we have three rings, then the intersection R4 is also a ring. Okay, so all of this we should prove it, but we are not going to prove it. Okay, just like that. Claim 2, the intersection of any family, the intersection of any family of algebras with a common universal set is also an algebra. Okay, so if we have some algebras and all of them have the same universal set E, okay, then the intersection of all these algebras is also an algebra. Okay, so we have we say that any intersection of, so the intersection of any family of rings is a ring, and the intersection of any family of algebras is an algebra. Okay, and now we can so this is the first theorem, lemma, how do we call it? Either claim. So this is a claim as well. Okay, so we have that for any family of sets. So let X capital be a family of sets. Okay, then there exists some ring that we call it like that, such that first of all we know that X is going to be a subset of R of X. Okay, and the other condition is that for any ring R sub 1 such that X is a subset of R sub 1, it holds that R sub 1 is a subset of R sub X. What? Yeah, I'm going to say that right now. So R of X is called the minimal ring containing X. Let me give you an example. What kind of semi-ring can we study? The semi-ring. So let me give you an example, and you will get all of this. Okay. Example. So let's take all the semi-intervals or half intervals. How do we call it? The set of all the half intervals in some half interval A, B. Okay, so we have some, so this is the real line R, the real line, not from R from here, real line. And we have A and B, capital A and B, right? So we have this half interval here. And let's take all the possible half intervals inside this half interval, right? So for example, this one, or this one, and so on. So you can take whatever you want. That didn't change, right? So we have this half interval, capital A, capital B, and inside this half interval, we are going to take all the possible half intervals, all right? All the possible. And this is a semi-ring. Why? So let's see. We need to prove that this is a semi-ring. So what's the first condition of a semi-ring? An empty set is different, right? So the empty set has to be an element of S. Why is this true? How can we show that the empty set is here? We can take just this. No, sorry, A. From A to A, so this is empty. Okay, so this is the first one. The second one is that the intersection, and of course the intersection of two half intervals is going to be a half interval. So it means that it's also an element of S, right? We have some A sub 1 here, and B sub 1, and we have some A sub 2 and B sub 2. What's the intersection here? The intersection is all of this. So a new half interval. Okay, so it holds for this one. And the final one also holds. Okay, so this is for example, actually the only good example we can have for a semi-ring. Okay, all the possible half intervals inside a half interval. Okay, and in this case, for example, this is a half interval with a universal set. Which set in this case is the universal set? This set, right? So the universal set is the set which contains all the other sets. Okay, so capital this interval. Okay, so we construct here a semi-ring with a universal set. Okay, now what do we have here? We have that X is a family of sets. For example, this one. Okay. It's not what I don't. Oh, right. R of X. Yeah, I forgot that. Yeah, sorry. So R of X, I'm going to explain that right now. Look, we have X. X is any set. For example, any family of sets. For example, this one. Okay? So we have this family of sets, which is a semi-ring. For this case, is a semi-ring. And now here we have that there exists, for this set, there exists some ring which contains this set, this family, and is the minimal one. So if we have, so this is X. This is capital X. For example, that one, the half interval, right? This is a semi-ring. In that case, is a semi-ring. And we have that there exists some R of X, so some ring which contains X and is the minimal one. So for any other ring, I don't know, for example, this one, R sub 1, this is also a ring, and it also contains X, but R of X is a subset of R sub 1. So R of X is contained in R sub 1. So that is why this is called the minimal ring containing X. Okay? And this is very important because we are going to define what the Borel sigma algebra is. And a Borel sigma algebra is the minimal sigma algebra containing all the open sets. So this word minimal is very important. Okay? So there exists a unique, and that's very important. Well, so there's this unique ring which contains X and also contains is contained in any other ring containing X. Okay? Clear? Yes? Good. Now we have that. Is it clear for you? Who's there? I don't know. No, okay. Oh, I can hear you actually. Good. My microphone was broken last time, so I was speaking and it wasn't. I see. I'm sorry for that, sir. Okay, good. What about Gabriel? Are you here? Yes, I am. Great. Yes, yes. Great. And what about Hasmin? No, she's not here. All right. Okay, we have that. And what else can we get? We have the same ring. Uh-huh. Yeah. Okay, so this is lemma number 1. 1. So don't forget, this is a claim, so we have to prove it. All of this has to be proven. We're not going to prove it. Okay, so we have semi-ring S and okay, so let S be a semi-ring. Okay, and we have the following set, which are elements of S. A is sub 1, A sub 2, A sub n, right? So all of these elements, all of these sets are elements of S, okay, such that A sub 1, sorry, A sub 1 and A sub n are subsets of A. Okay, so the same thing here. We have A, and we have some subsets of A. This is A sub 1, A sub 2, up to A sub n. And they don't intersect. So the intersection is empty for any I different from J. Okay? And we state that there exists then the following set: A sub n plus 1, A sub n plus 2, and the A sub m, right? So here I can change the color. Okay, yeah. Also elements from S such that A is going to be equal to the disjunctive union of all of these sets, right? From 1 to m of A sub I. Okay, so we have here A n plus 1 up to A sub m. Okay, so every time we have some set A and we have some subset of A and all of them are elements of S, then we can get a collection of sets which don't intersect, and the union of all of it is going to give us A, right? This is quite simple, but it's very useful. Okay, you will see why. Then we have to show what. There's a lot of things here. Okay, yeah, this one. So this is the first theorem, but this is important. This is the first theorem. Hmm? These can be empty, yes, of course. All right. Okay. So the theorem. What do we need to show here? We need to show the following: that if we have S, so S is a semi-ring. Okay. For example, the half intervals that we already have. So we have some semi-ring. Now from here, we need to get something bigger, so a ring. So how do we get a ring from a semi-ring? And that's what we need to get here. So R of S, so this thing from here, this is the minimal ring containing S. So this is the minimal ring containing S. Okay, the same way that we talk about the X, right? The minimal ring containing X. Now we don't have just X any set, but we have a semi-ring. So we have some collection of sets, which is a semi-ring, and we want to know what, how this set looks like. So how does this ring looks like? And this is actually just the following. So this is the disjunctive union of all the elements of S. So here we have that I is just 1, 2, n, A sub 1, A sub m are all the possible elements of S. So what do we have here? We have a semi-ring S, and in here we have these elements, these sets, A sub 1, A sub 2, A sub 3, or no, something like this, and so on. They can intersect. Thank you. Yes, sir. Has been okay. All right. So we have this semi-ring S, right? And we have these elements, okay? And this is a semi-ring. How do we get from here? How do we get a ring? And how do we get actually the minimal ring containing all of it? So all we have to do is to take all the possible disjunctive unions of all the possible disjunctive union of all the collection of sets of S. Okay, so let's take, for example, this one. So A1 and A4. So this is going to be an element in here, and this one, okay, with a different color. And this one, for example, A sub 3 and A sub 4, this is going to be an element in here. And all the possible unions are going to be elements on the ring, okay? The minimal one. So we already know how to construct any ring that we have. So again, if we have this semi-ring, sorry, so we have A and B. So we have the semi-ring of, no, like this, right? Open here, open, and here's open. So we have the semi-ring of all the half intervals. All we gotta do to get the ring from here is to unite all of them, right? The disjunctive union of all of it, it will give us this. Okay, good. Now we already have a ring. So we have a semi-ring. Yeah. Sure. But let's do it at the end, okay? Because we lose time. But all right. Okay, and now, what else do we need? Oh, we have a lot of, and no, we are close. So we have this R of S, and yeah. So this was a theorem. Now we have a lemma here, and it's the following: that if we have, okay, so we have S. This is a semi-ring, right? We have a semi-ring, and we have this collection of sets of S, right? Such that, in A is here as well, such that A is just the union from 1 to n of AI, right? Then no, we don't need this, sorry. We don't need this A here. Just this. Okay, so we have these elements A1, AN, then there exists some collection B1, Bn, such that for every I, it holds that AI is equal to the disjunctive union of some AI. sorry, bj. So this is b. Okay. bj. So what does it mean? It means that we have, for example, something like this. So this is A1, this is A2, and this is A3. Yes? All of these are sets of S, elements of S. So what we can do is we can, each of these sets AI, we can express it as a union of other sets of S. So we can take new sets. So for example, we can take this set from here. Let's call it B1. We can take a different set, B2, and a different one, this one, it's going to be B3, right? And B1, B2, and B3, and B4, and B5, B6, and B7, right? So like this. So they don't intersect. We can see that for every AI, we can express it as a union of some B. And all of these sets are elements of S as well. Okay? So we can decompose these sets into other sets. All right? Good. Next, why do we need all of this? Let me show you. All right, so we finally came to a new definition here. So we need to define what the sigma ring is and the delta ring. So definition of the sigma ring and delta ring. Okay. So, and from here we will get the definition of a sigma algebra, of course. Now, a family R of sets is called a sigma ring if, so the first condition is that R is a ring. So it means that every sigma ring is a ring, okay? And the second condition is that for any countable collection of sets, a sub 1, sub 2, sub 3, right? From R, it holds that the countable union is also an element of R. Okay? So this is actually from, if you look at this, you will get the definition from a sigma algebra, right? The countable union of the elements of a sigma algebra is an element of a sigma algebra. So we have here the countable union of the elements of a ring is an element of a ring, right? So let me write that belongs here like this. So this is the definition of a sigma ring. And with a beta ring, delta ring, right? So this is for delta ring. The difference is that we don't need the union, but we need the intersection, the countable intersection of sets. So for any countable collection of sets from R, it holds that the countable intersection is also an element from R. Okay? So that's the difference, right? Mm-hmm. Mm-hmm. Look, each of these elements, a sub I, is an element of R, first of all. So they should be an element of R. And the union of this infinite number of elements is also going to be an element of R. Okay? No, they should be an element of R. That's written here. That's a, well, that's not okay, because in that case it means that they are not element of R, because we already proved that for any A and B, the union of A and B is an element of R, right? So if you get that A sub 1, A sub 2, this union is not an element from R, it means that A1 and A2 is not an element from R, I think. No, A1 is a set, right? The set of, uh-huh, yeah. Mm-hmm. Yeah, please. I just don't get it.
Yeah, this one we already proved last time.
Mm-hmm.
But based on what you wrote here, I'm asking if the set of, that's what you wrote here, right?
This means this. A1, A2, and AN and so on, right? This means this. Is that clear, right?
Not the set of.
So this means the set AI, the elements AI from 1 to infinity, right? So all of this. Yes?
Yeah. From one, this the element from A1 to A infinity, right?
Yes. And each of these elements, each of these sets is an element of R. Not the union or something, just each of them. That's the meaning of this. And then I said that the union is an element of R. Yeah? Okay, good. Clear for everyone, yes? Okay. So that's the definition of a sigma ring and a delta ring. Okay? Now, what do you think is a sigma algebra then? A sigma algebra is just this, but in the case when R has a universal set. Because if R has a universal set, then R is an algebra, right? And if we have an algebra for which all of these holds, I mean, this holds, then we got a sigma algebra. And if we have an algebra for which this holds, then we got a delta algebra. So we don't have only sigma algebras, we also have delta algebras. Okay? So let me write that here. In the same way, we define sigma algebras and delta algebras. So the difference is that we have the universal set container on this ring. Okay? What's the difference or something? The difference is that for a sigma algebra, the sigma algebra is closed under the union, under the countable union of elements, union. And the delta intersection is closed under the countable intersection of elements. So sigma means union, delta means intersection. Okay? And why do we need all of that? Well, because, and that's what we have here. Let me Let me see it. Let me show it. The following claim that if we have a sigma ring, then this is, let me just, by the way, let's change it by black. Then we get a delta ring. So a sigma ring is a delta ring, but a delta ring is not a sigma ring. Okay? And now with an algebra, a sigma algebra is a delta algebra. Sigma algebra is a delta algebra, and delta algebra is also a sigma algebra. So they are equivalent. What does it mean? What can we do with this? Well, if we want to prove something for a sigma algebra, maybe sometimes it's better to do it for a delta algebra. It's going to be easier to do it for the delta algebra. And if it's true for the delta algebra, then it's going to be true for the sigma algebra. Right? So that's why we need this. Okay? And this one, let's prove it, because it is important. Okay? So we have 10, 15 minutes more. How do we, let's prove this. So let's have some, so let's call this number 1 and number 2. Okay? So guys, if you have any questions out there in Zoom, don't forget to ask. All right? No problem. Okay, good. So let's prove this. Let's prove the first one in that direction. So how do we prove that this is not true? So we have to give a counterexample, right? So for the first one in this direction, so this is not true. Yes. So let's take the following set. The set of all the finite elements on the natural numbers. All finite, sorry, not elements, but subsets. All finite subsets of n. Okay? So, all finite subsets of the natural numbers, right? So I think this is clear. Now, is this a delta ring? Yes, because the intersection of any subset of the natural numbers is a subset of the natural numbers, right? So we have, for example, the set 1, 2, 3 and the set 1, 2, 3, 4, 5. The intersection is going to be 3, right? 1, 2, 3, and this is an element of A. So we can show easily that this is a delta algebra. Now, why this is not a sigma ring? Why this is not a sigma ring? Because take, for example, all the singletons of the natural numbers, right? So take, I don't know, 1 and 2 and so on, right? The union, the countable union is going to give us what? The countable union from 1 to infinity of all the singletons give us what? N. No, n, right? These are finite, right? So we obtain that the countable union give us n, but n is not an element of this set, so this is not a sigma ring, right? Yeah, is it clear? Okay. Now, so this is good, all right? So this is what part exactly? Because for this to be a, sorry, not sigma, but delta. No, sigma, yes, sigma. So If this set is sigma ring, it means that the countable union of elements of this set is also an element of this set. And the countable union of these elements give us n, the set of all natural numbers. But A is the set of all finite subsets. So n is not a subset of A, right? Because these are finite. Right? What? All right. Do you remember the difference between countable and uncountable? Yeah. So. Yeah.
So we have some little n, which is the final number of n.
Yeah, but
So if we take the union of all the sets of I, it's going to be all the numbers until that little n.
yeah.
Be the whole number line.
But we can take all natural numbers. No? So think of any number, natural, as big as you want. This is going to be a subset of A, right? An element of A, no?
If we take A as all the subsets of the natural number.
Finite subsets.
Finite.
Yes, finite. So you cannot take, for example, all the numbers greater than 5, because this is infinite, right? So you can take only finite. Whatever, 2 millions, but finite.
Right. It's not going to be n to take the countable union. It's going to be finite.
No, because it's the countable union. So do you remember what the countable means? So we have finite and infinite sets, right? Finite is just finite, right? And for infinite, we have countable and uncountable. And countable sets are which one? Famous countable sets. The natural numbers, which are infinite, not finite, okay? The natural numbers are infinite, but countable. It means that we can count them somehow, right? The set of all the rational numbers are countable as well, but the set of all the real numbers is uncountable, right? So it means that this set n is infinite, countable but infinite. So if we take, we are taking this 1 union 2 union union n union all the natural numbers, then this gives us n, right? The set of the natural numbers. Yeah, but we're taking here all the finite subsets. So this is not. Okay? Good. If you have a question, then ask. Okay? All right. Good. Now, let's prove then. Let's prove that we can have that if we have a sigma ring, then we will have a delta ring. So what does it mean? It means that we know that we have a sigma ring. So the union of countable number of sets belongs to this set, right? We know that. So how do we get sorry. Yeah. How do we get this, the intersection, using the union? So for example, we have symmetric difference. No, the symmetric difference. All right, let's do just step by step here. Let's finish this and then we'll finish, all right? So we have here a sub 1 Here, this can be a sub 2, a sub 3, and a sub 4, and so on, right? So what do we need? We need this. Yes? The intersection of all of them. So let's take from, let's find this. All around this, okay? So how do we find that? It's going to be the union of a sub 1 minus a sub I from 2 to infinity, and from here we take a sub 1. Color, right? So every time, for example, in the first one, from A1, let's take out A sub 2. So we will get, this is A sub 2, so we will get this. Yes? From A1, we take out A sub 2. Then from A1, we take out A sub 3. Then we get this. Where is it? Yeah? And so on. So at the end, the union of all of it give us this yellow thing here. So everything around this. And then we finally, from A1, take all of this out, and we get the intersection. From 2, yes, it's from 2. From 2. Okay? Good. So this is the first one in that direction. All right? And now for the second one in this direction, so if we know that we have a delta algebra and we want to show that this is a sigma algebra, so we need to do just, if we have the intersection, we need to get the union, right? How do we get that? So, how do we get all of it? The union. We need, so we know that this is an algebra, so it means that we have the universal set, right? So in this case, we can change this by the universal set, right? The universal set contains everything. And now we need to take out all of this. Let me do it just again. I need to take out from E all of it, all of this. Yes? If I take out from E all of this, then I will get the union of, this is A1, A2, and so on, right? So how do we get all of this? Well, the same is in the intersection here from A1 to infinity of E minus AI. Yeah, so from E, we take out something. We take the intersection of all of it. We'll get this and then this. And this is the proof, right? So if we have some delta algebra, so it means that this is a sigma algebra as well, because we can express the countable union using the countable intersection. And in the other way, it's just exactly like this, but instead of writing A sub 1, we write E in this case for the sigma algebra. Yeah. Mm-hmm. Yes. Okay, good. So that's it for the lecture. Is everything clear? Do you have any questions? Yeah. Okay. All right. So check that home in home. We will continue next class with the theory. So I thought that we will finish this by now, but no, we won't. So we still have like one lecture on this. Okay. So the first problem. Okay. So sorry, what again? I don't. Do you have any right now with you? No. I just don't have it. I would have to buy it. I don't want. Yeah. So if you can get, of course, and you can get everything from here. How I have no idea, but you can get it if you want. I just don't. Oh, I don't think so. Well, but last lecture is we didn't. Yeah. Well, I think we can save this somehow. We will check that when we finish. All right. Anyway, you have the recording on YouTube, so yeah, sure. Yeah.
I think I can start now.
Okay, good. Let's listen to you.
Yeah. So as for the question states the following. A point is randomly picked inside of a rectangle of size 1 and 2. Find the probability that the distance from this point to the nearest side is less than the distance from the point to the nearest diagonal.
All right, so we have a rectangle here. We have the diagonals, and we pick randomly some point A, right? And we have to find the probability that the distance from between A and the nearest diagonal, yet, and the nearest side is less than A and the nearest diagonal. Good. So is it clear for everyone what we need to do here? So the statement of the problem is clear for everyone? Okay, good. Now, how do we solve it, Daniel? Please.
Solution to this question, but I went by using geometry to solve this question.
Yeah.
So what I did, first thing, I created like two straight lines. How can I say it? So so if you can see the picture that I sent you, so
Yeah,
like
I saw it.
yeah, and I started working with one part of the triangle. So suppose we're going to work with the quadrant where you wrote one on. So this is the triangle that you're working on first.
With this one, all right.
The first, yeah, it doesn't matter really.
Mhm.
So by using geometry, we know that if we divide the triangle correctly, we can get it. We can break the most left triangle into an angle. Suppose it's going to be, let's call it 2 alpha, and break it into 2 equal angles, alpha and alpha.
So this Wait, let's do with a different color. Sorry, just different color. Blue, right? So here we divided, so we had some beta here, and we divided into two angles, alpha and alpha. So beta is equal to 2 alpha, right?
Yes.
Okay, good. What's the name of this line, by the way?
Sorry. Memorizing this.
All right. Yeah. So, and why do we need this?
Well, because if we can find, see, if we create this line, if we can create this line with the next dot, if we do this, yeah, and we find all of those small triangles, all of the four big triangles, this is basically the area. If we land in this area, it's going to be closer to the line than the diagonal, basically. That's what it's going to be.
Yes, because here, in this point, on this point here, the distance from this line to this point, let's call it x1, and the distance from this point to this side, let's call it x2, is equal, right? Is equal. So all we gotta do is to, this is true for all these points. So we need the area where a point is nearest to the side. So all the points over here. So we care about this area.
Well, this area should be 2 multiplied by 10, or 10 1 half over 2. That's what I want it to be.
All right. Yeah, so this area. Right? So we need to find this area, and we need to divide it by 2, right? The area of the rectangle. And this will give us the probability. The exact value, I don't know. Well, yeah.
Either, so I don't know.
Let me see what you found. You found this, so that the probability is. You have to check that by yourself, all of you, because I don't know the exact answer for this also. So it's 4 plus 3 square root of 5 over 7 plus 3 square root of 5 over 2. So this is the answer that Daniel found. You can check it, but the idea is correct, and the main thing here is the idea, because to find this is a long story, so we are not going to do it. All right. So yeah.
I had the same idea, but I found the area differently.
Right. How?
Basically, like if you can't come. So that my idea is. So obviously, like if this line, if we continue it, is going to come to here.
Mm-hmm.
And
wait, but you mean how to find this area?
Yeah, or to find the area.
Ah, right. Yeah, there are many different ways, of course.
Yeah, I mean, should I discuss it? Or?
Yeah, please.
Well, my idea was like if we continue this line up to here. So let me just do like this, and obviously we can continue this line here, right?
Mm-hmm.
And now if we look at this part of the rectangle, so we can divide the whole rectangle into 2 rectangles, and you can see that these are actually diagonals for this rectangle.
Yeah.
And this area is 1/4 of this rectangle. Well, you know, like it's like you take a square and you take 2 diagonals.
Yes.
So this area in green is 1/4 of this area, and the same goes for this. And for
1/4 of this area.
Well, right. So like.
Why?
I think so. Like if you have a square and you divide it like this, I mean, this is 1/4.
But each. For a square.
Well.
We don't have any square. I mean, maybe you're right, but these are rectangle. All right, because we can divide this into squares, right?
To find this part,
but
we divide like this,
Yeah, yeah,
Continue these lines here
Yeah.
and here. And this is also 1/4.
Yes, 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 yes.
So, but I didn't get such a complex answer. I got like something simpler, but yeah, it's like you partition. So the main algorithm is you partition the whole rectangle first into two smaller rectangles,
Yes.
which is 1/4, and then you do the same thing with two squares and also 1/4.
Yeah, I think it works. I
But
think
what
it's
answer
correct.
do you have the actual?
I don't have the answer. That's perfect. I haven't computed. So let's do the following. Compute your answer. I will do it as well, and we compare next week. All right. Which one is correct? Okay, good. So is this clear for everyone? Yeah. Okay, good.
Yes.
Great. Now, the second one. That's right. Yeah. The second exercise. For the second exercise, who wants to solve it? All right, please. So tell everyone what do we need to solve and solve, please.
We need to find.
Let me then find it over here. We have an n-sided die and an m-sided die, right? Two dice with sides n and m, right? And we need to find the probability that you get an even number and an odd number.
What I think the idea is it's either n is odd or n is even. And
Wait, we don't know if n is odd or even. Okay, you are looking at, but you have too many options, 4 options.
yeah. So it's either this, or this.
Wait. Look, we have 2 dice, and so the first die has n sides, 1, 2 to n, and the second one has actually m, 1, 2 to m, right? We throw these dice and we get a number from 1 to m and from 1 to n. Yes? Okay. And then what? So
like I said, either n is odd and m is odd.
you mean m or the number that we get in this die?
No, m, the number of sides.
Okay, but wait, but we have all right, yeah.
So for example, in the first case where n is odd and m is odd, that means, let's say the number of sides is 7 and number of sides for this die is 5.
Okay.
Second case, maybe n is 6 and is 5, or that's what I mean with the number of sides.
Yeah.
So in that case, there are 4 possibilities.
In that case. But these are not all the cases, right? So
There are cases.
no, what if both are even or both are odd?
So if both are even, m is even, m is even.
Okay, I see. And then what?
So then you can calculate the probability in these 4 cases and sum them up.
Okay, let's try to do it that way.
So if n is odd and m is odd, the probability of getting an even number if n is odd. Let's assume we're going to okay, first two choose 1. This will determine if we're going to get the even number from the n-sided die or the m-sided die.
Why? So from 2 you are choosing 1. What you are choosing? What are you choosing here?
Which die we're going to get the even number from.
Okay.
multiplied by, if n, let's assume we're going to get the even number from, it's even more complex than I thought.
Yeah, it's too complex.
But I forgot about choosing which die is going to have the even number.
Only 4 cases left.
Yes, only
odd.
But which die will have the even number?
Don't forget that we are not getting n or m. We are getting a number from 1 to n and from 1 to m. So what you're doing, this is too complicated. Maybe you can get it somehow. Yeah, that's how you have to start. All right. So you can just okay. Oh, you're gonna spend all. You can just get a new. And that's it. All right. Yeah. Look, what do you need? What you had before, or
no.
Look, you have 2 cases. Only 2 cases. In the first case, you get an even number from the first die and an odd number from the other. In the other case, well, the other side, right? So let's consider these cases. So this is the first case and this is the second case. So in the m side die, you get an even number, right? And in the n-sided die, you get an odd number. No, n is not odd. From the yeah, but don't write it like that because so from like this, from n-sided die we get odd number. Okay?
Okay.
Now, how many possible odd numbers do we have from 1 to m?
So for getting an even number.
All right, it's even, right? How many even numbers do we have from 1 to m?
That has 2 cases. If m is odd or m is even.
In general.
Oh, in general, then it's going to be. But you might not get
n by 2 and what else?
Except to use floor function.
Yes, exactly. What do you want to use? Don't be scared about the floor function. You're a computer scientist.
Yeah, exactly. I don't think. Yes.
No. Why? That's the way that you have to do it.
Yes,
That's much more complicated, of course.
We need to sum that the case when m is.
Look, every time you have to look at the more general case. The more general case is m is any number. So look, m is any number, any. So
we shouldn't use cases.
So look, how many? This is the question. How many even numbers from 1 to m?
Yeah, this is floor of m over 2.
That's it. You have a number. Why don't you like that? So the number of even numbers. Because what? That's it. All right.
Okay. Yeah.
So now, how many odd numbers do we have from 1 to n?
That one will be ceiling of n over 2.
Right. So what's the probability that in this case we get an even number and an odd number? And in this case, the first case.
So this probability of first case.
Well, n times m times m.
Probability that we get m even in m-sided die is m over 2 over the m possible outputs and multiply by. So
now, in the second case, what's the answer in the second case? So in the second case, we get an odd number from the m-sided die and an even number from the n-sided die. So we get what? I mean, yeah, you can write it right now. All right, so now what's the answer for this? That's it. All right, so.
But cases is more interesting.
What? I mean, you have to solve many exercises using this function. In computer science, you use this function every time, as far as I remember, right? So don't be scared from using this function. It's just like that, okay? So yeah, it is clear for everyone? Yeah? Okay, good. Now the third one wants to solve it. I don't remember which one was the third one.
Maybe I can help you with the third one.
All right, sure, yeah.
Okay, so the third one said that a man is known to speak the truth 3 out of 4 times. Then he throws the dice and reports that it's 6. What is the probability that it's actually 6? So yeah, we know that probability that he speaks the truth is 3 from and the probability that is false is 1 minus the probability that is speaking true. So it's 1 minus 3 4. Right?
Yeah, so probability that speaks false is just 1 over 4.
Yeah. And what probability that in general, if we throw a dice, the probability that we get 6 is 1 6.
Mm-hmm.
1 6.
Yes.
And the probability of not getting 6 is 1 minus 1 6, which is 5 6.
Yes.
So knowing this, we can use the base theorem, and we can compute using those.
So, what conditional probability we need to find?
So we need to find probability that let me see 1 second. We need to find the probability that is let me think. We need to find the probability.
So here we have some conditional probability, right? Because we want to use Bayes' theorem. So what do we know? We know that he said, yeah, sorry. We know that he said that he got 6, right? So let's say that that's here. So let's call B that, so he said 6, right? And we want to know the probability that actually it's 6. So let's call this event A. So we want to find the probability that actually he obtained 6 if he's telling us that he got 6, right? Okay, so for this, just 1 second. So what do I need to write here? Not for you, Gabriel, but for everyone here. So the Bayes theorem, what should I write here? So A intersection B, right? And here, probability of B, right? So what is the probability of A intersection B? is the probability of B given A times what? Probability of A. Yeah. And here what is, well, the sum of, so B, what is B? B is that he said A. So how many cases do we have? That he's lying or he's saying the truth, right? So let's call B1, he's lying. What's the right line? Sorry, line, like this? I'm not sure. And the B2, he's saying the truth. Yes? So here we have to write the probability of what? For everyone, for you, Gabriel, also. So here B given. Yes? Okay, now let's compute everything here and we get what? So what's the probability? What is the probability that he said 6 if he obtained 6? 3/4. Now, what is the probability that he obtained 6? 1/6. Right? Now, what is the probability that he said 6 if he's lying? So he's lying. And wait, yeah. 1/4, right? Probability that he says 6 if he's lying. 1/, oh wait, it's 4, so it's 6. The probability that he says 6 if he's lying. 1/4? Yeah, so that would be here. Yeah, so that would be this, 1/4. This is something else. Right, so this one. Yeah. So this is the probability that he got 6. No, the probability that he said 6 if he's saying the truth. So 3/4. And then what is this? The probability that he's saying the truth. Yeah. The probability that he said 1/6, the probability that he said the truth. One by 6. So here. So here, right? He's lying. And here 1/6. Yes, and 3/4. Yeah? Yeah, I think it's correct. So here is the probability that he obtained 6. No, that he said 6 if he's lying. So he's lying. All right. I see. Yeah. So what's the probability that he didn't get 6, right? So 5/6. Yeah. Yeah. Is it clear? Again, please. Yeah, the probability of B given B1. So B is that he said 6, but he's lying, given that he's lying, right? Five over 6, yes. Let me. And here we have 1/6. Here we have 1/6. I think that's correct. Okay. So thank you very much. 2/4, 1/6, and yeah, it's correct. Okay, is that clear for everyone? Yes, good, perfect. Next, we have, thank you very much, Gabriel, and now we continue with the 4. Oh, this one is not easy. So let me continue over here. Who's next? Okay, let's see who's the first on the list here. So the first is Krutika, but she's not here. So the second is Santiago. Please. Well, let's try it together. Come on, please. So look, it says that. Let me. So we have two players. For example, play A and B. All right. And the first one rolls 3 dice, and the second one 2 dice at the same time. And they do that until they obtain 6 on at least one of the dice. Find the probability that 6 was rolled by player A and not by B.
The first die is the first player rolls 2 dice or 3 dice?
3 dice.
And the other?
2. So let's do the following. Let's denote a new event, A sub k, and this is going to be the event that the number 6, that we obtain number 6 in the kth time. All right? The kth turn, how to say. Okay, we obtain kth time. All right. Now, so yes. Now, what do we need to do? Let me check. Don't remember. So let's. Yeah. So we have two new events. BK and CK. All right. And BK is the event that in the kth time, the player number A got 6. All right. And CK means that in the kth time, player number B got 6. Okay. So you remember that. Now we need to find the following probability. What's the probability that we got BK intersection with the complement of CK? So what does it mean? It means that the first player got 6 and the second didn't. Right? So how do we find this probability? Yes. So what do we know about this event and this event? Independent. Good. What does it mean? We can multiply. All right. Please write that. Now let's find these probabilities. So what's the probability that player A got 6 on the kth roll that he did?
It's the distribution that we put the times that we throw a dice, for example. I don't remember which one.
Don't think about that. Just think about what's the probability that he got 6 on the first one, on the first time. So he has how many? 3 dice, right? What's the probability that he gets 6?
1 over 6, 1 over 6. So we multiply it
What?
or not?
Well, 3 dice. He's yes, just one have to be 6, but he is rolling 3 dice. One minus 5 over 6. 1 minus. Okay, so let's find this probability. What's the probability that he gets 6 on the first one, on the first case?
1 over 3 multiplied by 1 over 6.
1 over 3. No. Right. Let's see that he gets 6. What's the probability that he gets 6? He needs at least 1. So this is fixed. So he needs, how many options do we have? 36. And how, no, 30, so 6 cube, right? And how many do we need? 5 square.
Why 5?
5.
Ah.
5. So how many? So let's just think about he rolled these 3 dice, right? Then what's the probability that he gets 6? So how many options do we have in total? We have 6 cube, right? So 6 times 6, 6 and 6 in every die. And how many of these are good for us? 5 square. Because actually no, because maybe we obtain 6 again. Okay, do you see it? Yes, the component here. Yeah, but yeah, so
We don't get 6 in all of them.
mm-hmm.
The probability of that is 5 over 6 cubed.
Mm-hmm.
The probability we have at least 1/6 is 1 minus probability of not getting any 6.
Yeah. See, yes, for this one now.
That's 1 minus 5 over 6, which is the probability of getting 6. But we don't know on which row he got that 6. So
we got it on the kth row, then it's 5 over 6 times to the power k minus 1. Yeah.
Mm-hmm. Well, this one. No? Yeah, no, it should be. So we obtain that, and yeah, it should be k, right? to the power of k. So we should have here k. No, because no, not k. Okay, please come here and thank you. You have also.
Not sure if I understand that question correctly. So as I understand, it happens like this, right? So at each time we roll 5 die.
Yes.
Okay. So okay, then if we roll it k times, then in these k minus 1 cases, we never get a 6.
Mm-hmm.
Okay, that means it is just 5 over 6 to the power 5, right? Because we are rolling 5 dice.
Oh, okay.
And none of them get a 6 to the power k minus 1. So this is for all the k minus 1 cases, and on the kth roll, this one will happen times this person getting no 6. I think that will wait.
Mm-hmm. Yeah. Okay. Yeah, that's for that one. But I just don't get why. Yeah, just something different here. I don't get it. Yeah, this part is correct. That's for sure. Well, all of it looks good. Yeah. So we obtained that. Okay. And now what? And now we are looking for the probability that. Okay. We are looking for the probability that which player wins.
Yeah, this should be the final answer, right? For k minus 1 cases, we rolled 5 dice, and got no 6. And on the kth case, this thing happened. So this is the probability that the 5k minus 3. Yes.
Well, after yeah, you subtract this 5. Well, it looks correct, but there's I just don't remember which part we have to. I will check this one, but it looks right. Something is missing. I just don't remember what. Right. So I will check that and we will see. Okay. Yeah. Do you mean in the number of k?
Uniformly count 5.
Yeah, that's the deal, but I don't remember how to put that over there. Yes, here, over here. Here, look. 1, You can change that from 1 to number 1. That's for that one. Here I have no idea. So anyway, we'll finish that next seminar because I don't remember and we can lose a lot of time. All right. All right. Now, do please the number 5 right away. Yes. Well, that was the easiest one. Yes. Number 5 is as follows. So we have a set. So the numbers from 1 to n. Okay. And we have a random variable psi, which is equal to the number of this set that remain in their places under random permutation. So somehow we have we change the positions of the numbers. Like for example, each of these numbers is just a student. So these are you, and somehow we change how you are sitting right now. And we have to look at the number of students which stay in the same place, right?
So Z is the number of staying in the same.
Yes. So what do we know about this random variable? So how can we express it? So we have n, no, not r, but n here, right?
Oh yes, sorry.
So we have n students, so we can express this psi as something. What do you think? Huh? Which one? What do you mean cardinality? Well, huh? Well, it's given, yes. It's the number of students of numbers which stays on their place after the permutation. It doesn't matter here. So we have 1, 2, but it doesn't mean that we have 1 and 2. 1 and 2 is just some representation. So 1 and 2 is students, all right? So, and what? What do you mean by that? You mean, okay, you mean this. Xi1, Xi2, and Xin. Yes? And what is that? So this is true, but what is the meaning of that? Yes. You're all right.
Like this much we can say either all of them are random or at max everything falls.
Okay, yeah. But what is this? Who can tell me? We did this many times previous semester, that's for sure. So, yes, indicator, random variable. What is the meaning of that? Is that 1 of 0? In which case we have 1 for this one, for example. Yes, exactly. Well, 1 if they remain in their place, right? Yes? No?
I didn't catch it. What happened?
So psi I is an indicator random variable. What's an indicator random variable? Okay, an indicator random variable is a random variable which takes only 2 values, 1 and 0, right? So 1 with probability p, some probability given, and 0 with 1 minus p, in which case it takes value 1 if I stays in its position, and 0 otherwise, right? Yes?
Yes.
So that is why this is the sum of this. So this is the sum of ones and zeros. And finally, we get the number of elements which state on the position. Now, what's the expected value of psi I? Mm-hmm.
So 1 times the probability that it stays in its position.
And what is the probability that he stays on its position?
1 times stay plus 0 times doesn't stay if you don't
Mm-hmm.
it. It is the probability it stays in its position. So it is probability. So number of permutations. So it's n minus 1.
Mm-hmm. So it is clear for everyone? Okay, good. So we have that. Now, if we know this, how can we find the expected value of psi?
So it is the sum of all of them.
All right, and that gives us,
Expected value of
yeah, so 1, right? Yeah, so m times 1 over n. Yes? We are summing up all of this. 1 over n plus 1 over n and so on. Well, not this, but the expected value of each of them. Then we get 1. So we actually did the exactly same problem last semester, if you remember. Exactly the same, but on that time we had letters and something else, and I don't remember exactly. Okay, now how do we find the variance? Mm-hmm. Let's find it. Mm-hmm. Okay.
So this is let me pick up. Not visible from my case. So this is equal to n times 1 over n square. This part, which is 1 over n.
What is n 1 over n squared? Wait, don't confuse. So we have this random variable. Now you can write the expected value if you want. So let's find the expected value of psi I squared. What's the expected value of psi I squared?
Expected value.
Yeah, so this is not 1 over n squared, right? We are talking about here the expected value. So don't forget about to writing the expected value of all of this. Now we need to find the expected value of each of these indicator random variables here. So we have the expected value of psi I squared, which is what? Well, 1 over n, right? Because we only have I, so 1 over n. So the same for here, right? It doesn't change. Why? Because we are multiplying 1 squared, so this is equal to 1 squared times the probability that probability, so 1 over n. So 1 over n, good. So we don't have here a square, but just 1 over n. So this is clear, so we get from here 1, all right? Yeah, 1, and what about this part? So how do we get, let's write it over here, the expected value of the sum of all, the product of all these random variables, which indicator random variables, which are different. So in which case, so what are the possible values for psi I and psi j? What are the possible values for each of them? 1 and 0. In which case, they both are 1.
Okay. That will be when both of them falls in the correct place.
Yes, exactly.
The probability is n minus 2 factorial divided by n factorial, which is equal to 1 by So this part is n times this one.
N times. How many pairs do we have?
How many pairs? That will be n square or n times n minus 1 by 2.
Well, you tell me.
If I am
They are different.
Not equal, then n times n minus 1 by 2.
And yeah, factorial over.
So we have 1 plus 1 over 2.
Actually, this should be 1 over 2 because the final answer is 1. So what is the deal here?
Okay.
Because this is 2 times.
If you take I is less than j, then 2 times.
Yes, 2 times, right?
Yes, then I is less than j.
Then we get 1. Wait, then we get 2. No, the variance is also 1, as far as I remember. Where's the mistake here, guys? Or maybe it's 2 and I just don't. Let me check. Somewhere here I have it. Well, because we have that this is 2, right? Yes. It's okay. This is 2, and well, 2 minus 1, right? Because this is just the expected value of psi squared. So so the variance is going to be 2 minus 1, which is 1. Yeah. Good. Here. What? Expected value of this, the answer is this. So is n choose 2? Well, actually, n choose 2. And we multiply by 2, yes. So n times n minus 1. Uh-huh. Mm-hmm.
Yeah, this is this part.
And that's it. All right. So is everything clear? Yeah. Okay. Yeah. Okay. Good. Now, let me.
Number is in place, number is in place. Can you get the expected value? Just with the probability that there's going to be a number in place.
What so the probability of, we know the probability is 1 over n. So that's the probability that any fixed number stays on its place. Yes.
All those n factorial permutations, there is a number that is in its place.
And all the others. Well, yeah. I mean, well, you have to change n factorial by n minus 1 factorial. Right? That's all the possible ways you can get this permutation. If one of the persons or one of the elements is fixed. That's what you mean, I think.
Do you remember the arrangements that we did last semester? Those questions that had to do with the arrangement.
Yes, this is that one.
And there's a formula for it.
Yeah.
So
Which one?
Yeah,
but don't forget that here we are looking at the expected value, not at the probability.
So we can't use it to get the answer.
So you mean that, so what's the probability that if we have n students and all of them change its position, what's the probability that yeah, that a fixed student stays on its place? Yeah, it's like, yeah, so we get something like e to the minus 1. Oh, no, wait. Yeah, yeah. Yeah, the inclusion exclusion formula. We use it. Expected value here. Well, what is the random variable in that case? The same random variable, so the number of persons that don't stay in their position. Yeah, the problem is different because xi in this case xi is the number of persons that didn't change. Sorry. Their position, right? This is what we are doing here now. In that case, we want to find the probability that at least one person, no, the probability that no, that the probability that nobody's, the probability that nobody stays in its position. in its initial position. Yes, that's the probability that we look there. So this is different. And so the deal here is that somehow we need to define a random variable using this, but this random, we cannot compute, we cannot like, or maybe we can, I don't know, we can think about that. This random variable somehow with this event here. Yeah, so number of persons that didn't change their position and nobody stays in their initial position. Well, all we can know is that if this is 1, then this is 0. That's it. We don't know anymore, right? That's it. So I don't know. I don't think we can use it. Okay, look, let's do the following. We can what? A break? But we have like 10 more minutes, 15 more minutes. I think we can just. Yeah, so this is an important example on how the probability space should, I mean, how the probability space is important. All right. So look, this is famous. This is called the Bertrand's paradox. The Bertrand's paradox. All right. Maybe you've heard about it. I don't know. So imagine that we have a circle, right? And in this circle, we have a unique triangle where all the sides are equal. So let's say A, and A, right? So we have a circle and we have a triangle on it. And it says the following. What's the probability that if we take some random, I don't, chord, maybe the name is chord. In Russian is horda. I should remember. A chord, right? All right, a chord, right? So if we take a random chord here, the length of this chord is going to be greater than A. Okay, so what's that probability? And this is a paradox because we can get different answers. Okay, actually we can get any answer from 0 to 1. That's very interesting. Huh? All right. So look, what's the deal here? The deal is that what does it mean randomly we pick a chord? What's your idea? All right.
If the chord
Mm-hmm.
is to the right of that A, it definitely means less than. If it's to the left, it definitely means.
Okay, this is one. So let's do it. So what you want to do, I think, is that we have to, how are we going to randomly pick this? Let's do it the following way. So let's pick the first point A. So this is A. First, let's choose A. And because of symmetry here, A can be here, right? So we can just move it. And now we have to pick randomly B. But let's draw again this triangle here. Oh. And now we have to pick B, right? In which case, the chord is going to be greater. So the length is going to be greater. If B is over here, if B belongs to this, how to say it? B is a point. Yeah, so we get this. So we randomly choose A, then we draw this triangle, and now we randomly pick B, right? If B is here, then of course the length of the chord is going to be greater than A. But if B is here or over here, then the length is going to be less. That's it. So what's the probability? 1/3, right? Yeah, because this length and this are equal. So the probability in this case is just 1/3. Good. Now let's do it in a different way. Okay. What if again we just here we have the diameter, right? D of the circle, right? And let's do the following. Let's choose any point on D. So let's say it. Let's say that this is the line D. Let's choose randomly any point, and this point is going to be exactly half of the chord, right? So if we choose this point over here, then the chord is this. Yeah. If we choose it here, then the chord is this, half. Right? So in which case, and we can draw the triangle again. Yeah, and we can draw it here again on this side. Let's draw on this side. So it means that, so this is A, right? So this distance is A, and this distance is A. So if we get the point over here, then the length is going to be less than A, right? And if we choose it here, below this, then the length is going to be less. Then what we need is this, this. In this section of D, every time we pick the center of the chord over here, the length is going to be greater than A, right? Yeah, is this clear? Now, all we have to do, so, and by the way, here we have the following, let me write that. So the sample space was just the circumference, right? And then A, the event A was the length of this circumference, right? So the probability of this was just A. So the length of A over the length of the circumference, right? So 1/3. Now here we have that this is 2 times the radius of this. So this is the center C. This is the center C. This is R and R, right? And if you compute it, we are not going to do it right now because we don't have time. So the length of this is 2R, right? Of the diameter is 2R. So the probability of this, let me write with a different color. So the probability of this is going to be 2 times R, right? 2 times R is here. It doesn't work here. No, I'm going to write it just again, and that's it. So the probability of all of this is 2R, right, over the length of this. and the length of this is r. You can compute it if you want. Okay? It's not very hard. So we get that this probability is 1/2. Okay? Is it clear? Yeah. So for the first case, we got 1/3, and for the second case, we got 1/2. And now we can actually do this again. And what if we have the circle here, and we have again this triangle. Yes. And we can have a circle inside this triangle like this. Sorry, it's not very. Yeah. And we pick randomly a point inside this, inside the circle itself. And if this point it's inside this blue circle, then the length of the chord is going to be greater than A. Because if we are here, for example, then this is going to be the chord, and this is going to be half of the center of the chord. So every time we pick randomly a point inside the big circle, and if this point is going to be half of the chord, and if this point is inside the blue circle, then the length of the chord is going to be greater than A. This is A, right? So to find this probability in this case, we need to find the area of this circle, A, and the area of all omega, let's call it, right? And this is going to give us 1/4 so far as I think I remember. So for 3 different situations, we get different answers, all right? So what's the problem? That's why this is called a paradox. But this is not a paradox. Why? Because we already defined the following. So in the first case, omega was the area now, but the length of the circumference. That was omega. In the second case, omega is the length of D, right? And in the third case, omega is the area of A. So in every case, we have a different omega. So it means that in every case, we have a different probability space. So the probabilities that we will get for each of these cases is going to be different. That is why every time that we have some exercise, we need to define this. We need to define what do you mean by randomly picking something, right? We have to define this, and we have to define the sigma algebra. Because if you define it in a different way, you will get a different exercise, a different problem, okay? So which answer is correct? All of them are correct. But that's because all the problems are different, okay? That's it. So do you have any question? No?
No, sir.
Good. Yeah, so I think that's enough for today. Thank you very much. See you next week.